Hi guys, so as promised, here's the video on the Zener voltage regulator for EC110. And the learning purpose of this video, why is it a learning purpose, not learning objectives? Well, the learning objectives is what you're ultimately responsible for in class, and I didn't want to add learning objectives in the video, so while this is largely the same thing, I called it the learning purpose. Alright, confusing, I know. Okay, anyhow, at the end of watching the video and spending sufficient time practicing, the students should be able to repeat the analysis in this video independently and derive the conditions for which the load voltage is equal to Zener voltage. Okay, the students should also be able to explain the IV analysis used and be prepared to attempt applying this technique for different problems. Notice I didn't say that this one video will teach you everything you need to know about IV technique, but you should at least develop the courage to attempt it. Okay? Alright, yeah, I know I promised, well, at least to Steve, I said that this video I'll do by last night, but as you can see, Professor Minin broke down and caught some Z's. Anyhow, it's morning now. Maybe some of you guys are sleeping, so it's still okay. Alright. Alright, so we talked about Zener diodes in lecture, and we saw that it's kind of like any other diode, except, let me see, do I get tools here? Alright, I think I'll just use the pen tool, because it's not clear to me how to get all the different tools in this mode. Alright, anyhow, regular diode has this turn on, but the Zener diode also has this breakdown in reverse bias voltage. Okay, actually all diodes have some sort of a breakdown, but Zener breakdown is particularly sharp. It's actually nearly vertical here, or a very nice corner. Okay, and we can also control the Zener voltage the way we build the diode. And that becomes very useful. So how sharp it is and the fact that we can control it in reverse bias becomes very useful in an application such as voltage regulator. So what is the voltage regulator? The purpose of the voltage regulator is to supply constant voltage to the load here. Okay. What might that voltage be? Well, it's going to be V Zener, of course. Even if the input voltage, okay, doesn't have to come from a battery, could come from rectified AC, could come from who knows where, okay? Even if this input voltage could come from logic circuits, for example, also varies, or this input effective resistance varies. Maybe we have long wires running from the voltage source to this to the load, and maybe temperature will change their resistance. And finally, even if the load itself changes, well, you can say, okay, of course we can supply this this voltage to the load as long as, probably the most obvious condition, that is that VI is bigger than VZ, okay, than the Zener breakdown. Notice we're biasing this diode in reverse, right? Okay, so if this voltage is bigger, it clearly has to be bigger than VZ in order to even consider the being in breakdown region. This input voltage, VI, has to be bigger than VZ. Okay, anything else? Yes, if you look at the load, what could the load be? Okay. Well, the load could be anything. What are the resistances you can think of? I can think of any resistance that's bigger than 0 and less than infinity. Okay? I can think of any resistance like that. Can I think of negative resistance? Well, that's actually something like an active device. That's a supply in itself, as you will learn maybe later in later classes. It's a useful concept of negative resistance, but it's certainly not a resistor. Alright, Okay, well, what happens if we have resistance that's 0? Okay, so if we have resistance, let's say this could be bigger or equal to 0. If we have resistance of 0, then this becomes just a short circuit. That's resistance of 0. And a short circuit, what kind of voltage does a short circuit has across it? Nothing. Has 0 voltage. So we can cross this out now. Okay, so it doesn't work for short circuit because we're clearly not going to deliver VZ to a short circuit. Okay, that's not something that's possible. So R has to be bigger than 0. That's our other condition that we know right away for sure. Our load is bigger than 0. How much bigger than 0? Well, we'll figure that out in just a little bit here. Okay, well, the first thing we can do is just simple nodal analysis, right? And what do we do first for nodal analysis? The very first thing we do is set the ground. And I think there is a very obvious node that we can set here. Really, the node is this whole thing, right? But we usually designate it with maybe a big fat dot like this. And we call this VZ because that's the voltage that we want to deliver, right? And that's the operating voltage of the Zener when it is in breakdown. Okay, the reverse bias voltage is VZ. All right, so now we can, what do? We set the currents, right? We can set this I1, I2, I3. Well, I think once you do that, you guys are pretty clear on what I1 and I3 should be. Now, that's not hard. We can write down I1 equals input voltage, that's V in, minus this node voltage, VZ, divided by R in, right? Okay, I3 is also not hard. That's just VZ divided by RL. Now, what do we know about I2? This is not a resistor, right? But here's what we know about I2. We know the IV characteristics of the Zener diode. It's something like sharp breakdown. This really should be on the axis. Okay, so that's the IV characteristics. And these IV characteristics, this by the way is V minus V Zener, and these IV characteristics are defined for the diode like this. The polarity here for the definition is like this. Okay, which is exactly reverse of the polarity that we have in our picture here. Okay, so in this case, actually, we should flip the sign of I and V, and so actually, our IV characteristics will become something like this. If we define I and V as we have it in the circuit. Okay? All right. Okay, so we know that we're going to be fixed at V Zener, but the only possible currents that we have in this configuration, the only possibility for I2 is that it's in this upper half plane right here. Okay, the condition is that I2 is bigger than 0. Okay, so when Zener is in breakdown, the only condition is that this current is going to flow in the reverse direction through the Zener. It's not the current that's going to flow the other way. Not this one. Okay? Not this way. All right. So that's all we actually need, because I2, we know something about I2 from KCL, right? Current law, Kirchhoff's current law. We know that I2 is I1, that's current into the node, minus I3. Alright, so then our condition, combining all of this, our condition becomes Vi minus Vz divided by Ri minus Vz over RL has to be bigger than 0, right? Well, really you could have 0, right? Bigger or equal to 0, bigger or equal to 0. Okay, so that's our condition. So let's continue the analysis of what that might mean. All right, and let me see. I don't know if I can erase this. You know what? How about we pause this video and you guys derive a formula here, and I will make a part 2 video and continue this. You guys start with this formula and just put it in a nicer form. For example, derive the condition for RL. Okay, so solve for RL. Meanwhile, I'll exit the video and clean this up a little bit. Okay? Is the video even running?